Next paper is HybridSVD when collaborative information is not enough, presented by Evgeny Frolov.
Thanks. Hello everyone. Thanks for staying late. I also would like to thank all the organizers to make this event happen. It's really exciting to be here. And I'd like to start my talk by listing some of the studies that compared current state-of-the-art models with some simpler baselines. And the general conclusion across those studies is that in some cases, proper tuning of simpler baseline models can give you comparable but even better results. We have also listened to a talk yesterday about the boring analysis of the progress that we're making in the field. And the question rises is, are we really making progress? Are those state-of-the-art models really flawed? Well, I guess not. It just presents that the problem that we're trying to solve is very complicated and hard and difficult. And there are many aspects that contribute into this difficulty. And one of those aspects is tuning itself. Tuning can be really hard and painful, well, I guess unless it's not your own precious model. As an example, take the number of latent features of the rank of matrix optimization. If you're working with like new dataset or with new algorithm, you typically don't know the range of the values that you want to tune. Also the training time depends on the value, and probably it will be a bit more restrictive against the higher values, and that's where the optimal configuration may be. And also the rank value definitely depends on other hyperparameters, so it's really unclear how to tune them together. And then can we improve this situation? Can we do better? Can we reduce these tuning puzzles? And well, you can probably think of like simpler models. Like one of the most famous is the PureSVD, right? It's just you replace your unknowns with zeros and then just compute single value decomposition of a certain rank, and then you have a very nice prediction formula, which is uniform. You can use it for predicting scores for non-users or for new users, as long as you have at least some of the user preferences. And PureSVD provides a number of unique advantages, and especially especially in terms of the rank tuning. So you don't need to compute your model for all possible rank values. You just compute your model once for high enough rank value, and then you just truncate your factors to obtain all the models of the lower rank. So it's very convenient, very easy, and for example, did you know that you can actually scale your SVD model to the billion size? If you didn't know that, check the worldwide criteria about that. Alright, so you can actually even improve SVD further. So there is a very simple way. Just normalize your columns or rows with their norms. Well, exponentiate into some factor, and this factor is another hyperparameter, but it's very easy to tune. It typically lays in somewhere between 0 and 1. It allows you to not only improve the accuracy of recommendations, but also the diversity of recommendations. It's basically you're trying to adjust for the power distribution, or power law distribution. Alright, so what about hybrid model? So we have lots of different techniques to make matrix optimization on neural network-based approach. It includes side information like user features and item features. What about PureSVD? So, and actually you can do this, and it's convenient to think about SVD as a solution to the eigen decomposition problem of the gram matrix of your original rating matrix. In that case, every element of the gram matrix is just a scalar product between the rows of your original matrix A, which is just user preferences. Which means that if, for example, you have two users who are like-minded, they have similar tastes, but they don't have any items in common, then the scalar product between their vector representations will be 0. Which means that the model cannot, the model doesn't know that they are actually similar. What you can do for this is that you can replace the scalar product here with some bilinear form, and the matrix S is some sort of similarity matrix. It's depicted here. So it encodes similarity between those items based on their features. Now, by doing that, you sort of create the virtual links between those items, and now your users will be closer to each other. So it's very simple. It's probably a very loaded slide, but it's all you need to do the computation. So your problem transforms into this generalized item decomposition problem, and there is a solution to it, and it's also based on SVD. So you just compute SVD not of your original matrix, but on auxiliary matrix, and then you also have all the benefits. You just integrate all the advantages of SVD here. And for example, you have also very simple formula for predictions, and you have simplified rank tuning. So it's very nice to have it. And there is an additional hyperparameter. There are additional hyperparameters, but they are still very intuitive. So there's, for example, this alpha. So it basically allows you to control how sensitive your model is to side features. If you put alpha equals 0, then it will be just pure SVD. If you increase alpha, you increase the sensitivity of your model to side features. And again, the range of values is small. It's a narrow range, so it's very easy to tune, and the model itself behaves smoothly regarding these parameters. Okay, we can also solve a false start problem as well. Well, actually, you can do it with PureSVD as well, and it's very easy to do. So what you basically need is to just find the mapping between your latent space and the space of your actual features. And finding this mapping in a general case for general matrix factorization is a very difficult task. But in the case of SVD, because we have those nice properties like orthogonality, we can solve this problem analytically. So you can analytically find this mapping and then use it to encode any of new called item or called feature or called user into the latent space. So it can be done very quickly, and again, all the computations are efficient. You can, as I said, you can do this for both PureSVD and HybridSVD. So here are some results. It's a lot of things going on there, but you can follow just those arrows. So first of all, you can see that debiased versions of PureSVD and HybridSVD are outperforming all other models. And here are optimization machines and local collective embeddings. So they are better than PureSVD, but the margin here is much smaller. What's interesting is that this matrix factorization here, which is basically factorization machines but without side features, it performs very well. And you may ask, okay, maybe we should use this model. And if you look at another method, which is sort of a proxy to the diversity of recommendations, you can see that this matrix factorization is actually behaves poorly. And our debiased versions are very good at it. They provide very diverse recommendations. So again, you're improving both accuracy and diversity at the same time. What about cold start? So in the cold start, the picture is similar. It's a little bit different in the sense that now both standard HybridSVD and debiased HybridSVD are outperforming all other models. Interestingly, that PureSVD, that's full start adoption of the PureSVD, outperforms factorization machines. Actually, in that case, for this Yahoo Music dataset, which is pretty large, we couldn't get factorization machines working. It just didn't converge. Okay, so you can see more results in this repository, and you can also run it right in your browser. So if you follow this link, there are instructions how to run at least some of the experiments, of course not on the largest datasets, but on smaller datasets. You can run it right in your browser. So to conclude, HybridSVD is a simple, very efficient and competitive algorithm. It has a number of advantages that are unique to this algorithm because of the use of SVD. And well, maybe it's not, definitely it's not, it couldn't be the best in all the cases on the datasets, but it can still be a very strong baseline that you could use to calibrate your own baselines or your own models that you will develop in the future. So with this, I would like to conclude the talk and ready to take your questions. Thank you.
you.